Hello everybody. In this video, we're going to talk about tangent planes and normal lines, which is from section 14.6. Alright, so maybe we can just recall what we have done in the previous video. So we talk about an equation of f of xy equals c. You can think of this as implicit function of y in terms of x. And this is, if we take a graph, then it is a curve living in a two-dimensional space. And suppose you're given some point, then you can talk about the tangent line and the normal lines. So the tangent line and normal line can be calculated. The equation can be found using the function z equals f of xy by thinking of this curve as a level set of this 3D function, which is like mountain surface or valley surface. And so if this is a level set, you can think of a contour map, something like that. And this normal line is parallel to the gradient f, and this tangent line is perpendicular or orthogonal to this gradient f. Now we're going to generalize this theory to f of x, y, z equals c. Then if we graph this equation, then we are going to get a 3D object, which is not curve, it's a surface, something like football. And if we are given some point, then we can talk about its tangent plane, not tangent curve, which is just touching the ball at the point, and normal line. And our objective is to find out the equation of the tangent plane and normal line. All right, to do that, we first talk about 3D function or three variable function f and unit vector, which is given by u1i, u2j, and u3k. This is actually a vector living in 3 dimensions, which we can write in this way: u1, u2, u3. Three numbers represent: u1 is x coordinate, u2 y coordinate, u3 is z coordinate. So here, if we have this 3D coordinate system, then we have unit length along each axis, and this is I, this is j, this is k. If we write down those ijk's, I stands for 1, 0, 0, j stands for 0, 1, 0, and k is 0, 0, 1. Okay. Now, so we have a function of three variables and a unit vector u1, u2, u3. Then along this vector can be thought of an arrow or direction, right? So if this is unit vector, this is directional vector. So given a function f and a direction u, we can talk about its directional derivative, or how fast does it change along this direction. This is direction derivative. To do that, first we want to find gradient f, which is given by partial derivatives. So the partial derivatives can be also written as fx, fy, fz. This is another way to write the vector, equivalent way. And what is the directional derivative? Directional derivative is dot product, so which is like this. So we can think of gradient f, we write fx, fy, fg, and dot product, the direction is given by u1, u2, u3, and then dot product gives you sum of those each product component wisely. That gives this formula. So gradient f is a vector, three-dimensional vector. In other words, the answer is three numbers. Directional vector, directional derivative is a number. If you calculate this, it's a number. And for the dot product, we can always, it's important to apply cosine laws. So if we have directional derivative, then this is dot product, which is product of two vectors magnitude times cosine theta, which is theta stands for the angle between gradient f and u, two arrows. And we know that the u is direction. In other words, its length is 1, so we can write this in this way. So when you have theta equals 0, then duf, the direction derivative, is gradient f magnitude, which is fastest increasing ratio. So if you want to increase f by moving certain theta degree, then what you want to do is theta equals 0. In other words, you want to move along this direction, gradient f. If you want to decrease the function value, then you want to take pi as theta for the theta. Then cosine theta is -1, and duf is its opposite. And this is fastest decreasing pace or decreasing ratio. So here is one example. We have f given by this formula, and p0 is the current position, and v is the direction. So we want to find the directional derivative of f at this point along direction of v. And the second question is, in what directions does f change most rapidly at p0? And what are the ratios of change in this direction? So from previous discussion, we know that if you want to change, if you go along gradient f, then it will increase most, and opposite side, opposite direction, then decrease most. So here, this actually asks for two questions. By change, they didn't specify increase or decrease. So for increase, we need gradient f. For decrease, we need go along this. Now, all right, so let's first look at what is gradient f. Gradient f is fx, y, z, and partial derivatives with respect to x is 3x squared minus y squared. And the second one, fy, is negative x, y squared prime is 2y. And for z, it is -1. And if I put p0 here, then that means x and y values are 1. So this is 3 minus 1, which is 2. And here, -2 times 1 times 1. And -1 is always -1. So this is the gradient. Now for the directional derivative, we need the directional vector, which is given implicitly by v. So we need to normalize that, because v length, if we check, it's not unit length. If we do that, then this is 4 plus 9 plus 36, 49, square root of, it's square root of 49, it's 7. So the direction you're moving to is normalization of v, which is 1 over 7, and 2, negative 3, 6. Now, what is directional derivative? Now it's ready to get this. So we have 2 to negative 1 to negative 1. Dot product, 1 over 7, it's a constant. I can put it in front of everything. And 2, negative 3, 6. And after computation, this is 4 plus 6 minus 6, 4 over 7. So this is directional derivative if you are moving along this direction. Now the next one is in which direction you move most rapidly. So for increasing, so we said this is asking for two questions. For increasing, we move along gradient f. But gradient f itself is not a unit vector, so we want to normalize that. So gradient f and gradient f length, which is, I'm going to write this, to save the space, I'm going to write this with negative 2j minus k over square root of gradient f length is 2 square, negative 2 square plus negative 1 square, which is 3. So it is 1 over 3, 2i minus negative 2j minus k. And the ratio is gradient f, which is from this denominator, it is 3. So this is 3. And for decreasing, the direction is given by, for decreasing most rapidly, it is opposite direction of this. So 1/3 negative 2i plus 2j plus k, and the speed is still equals 3. All right, I have to correct the here. So decreasing ratio is still, we want to put it as positive sign, because for the ratio, as long as we specify theta opposite side, then in that direction it is always positive. So the length is its speed. All right, we don't need this one. Our tangent plane. So now we're going to talk about tangent plane. First, we need to introduce the definition. The tangent plane to the level surface of this equation at the point P0, where the gradient is not zero, is the plane through P0 normal to gradient f P0. So this is normal line, gradient f with P0. So normal line is normal line of the surface at P0 is the line through P0 parallel to gradient f P0. So if we look at this, we will think of this as a rugby or any football shape, 3D object. And if you have a point here, the tangent plane is something like this, and the normal line is something like this. All right, how to find it? So the normal line is parallel to its gradient. Tangent plane, it's perpendicular to the normal line. So the formula is given in this way. So this is tangent plane. This is normal line. But instead of just memorizing that, we can think of what it looked like from the picture. So here, this is P0, which is x0, y0, z0. And if you take any point on the plane, right? So suppose this is xyz, xyz. Then the arrow connecting these 2 points is perpendicular to this normal line, which is perpendicular to the gradient f. So this connecting line of 2 points on the tangent plane is given by x minus x0, y minus y0, z minus z0, and it's perpendicular to gradient f, so which is fx, fy, fz equals 0. Then this is exactly the equation because dot product means summation of 3 products, which is specified as a formula in 1. Now the second one, normal line, this is also straightforward. So we know that suppose there is a point here, which is x0, y0, z0. It's a point on the surface, and there's a normal line. Then this is in the direction of gradient f. So in other words, the speed in x direction is fx, speed in y direction, speed in z direction are given. So at the beginning, you are standing in these points. So your coordinate, x coordinate, y coordinate, z coordinate. After time t, you change that much in each direction. So that's why we gave x, y, z in the parametric form. This is easier. And this is a line, this is plane. All right, having this in mind, we're going to look at this three-dimensional function, which is given by x squared plus y squared plus z minus 9 equals 0 at the point 1 to 4. So if we use MATLAB or Desmos, then you're going to have this kind of upside down cone. It's not really cone, it's paraboloid. And then we're given 1 to 4, a point in the surface. We want to find out the tangent plane and this normal line. All right, so to compute that, again, I encourage you to derive everything without formula, memorizing formula. So for actual computation, we don't need the picture. So we can think of this as, we can look at this as z equals f of x, y, no, so z, not z, actually w equals f of x, y, z. And so w is x squared plus y squared plus z minus 9. This is three variable function. W is 3 variable function in terms of x, y, z. And this surface, which is the picture is from here, this surface can be thought of level set of this 4-dimensional graph. This is 4-dimensional graph living in 4 dimension because there are x, y, z, w's if you graph it. But if you look at level set, that goes to 3 dimension. So this is level set. All right. Now we know that for the tangent line, it is wx, wy, wz, x minus 1, y minus 2, z minus 4. This gives you tangent plane. I'm going to leave it to your exercise to simplify. Another one is normal line. For the normal line, x at the beginning it was here, and This is wx times t. Y is 2 at the beginning and wy at t. Z is 4 plus wz at t times t. And you want to calculate for the normal line. All right, that's pretty much everything for today. And